right, good morning and welcome to Team 2's presentation of our senior design Second Avenue Bridge. I'm Emily, and to my left are team members Samantha and Claudia. First, for the agenda, we will offer a brief overview of the entire project, discussing the location, project constraints, and background information. Once that is completed, we'll then go into a detailed discussion of our structural analysis and design for our concrete footing and steel framing. After that, we'll discuss the traffic analysis portion of our project, which includes the design of detour routes, sustainability, and the analysis of alternatives. To wrap up, we'll discuss the detailed cost estimate and give our final recommendations for our project. First, the location. Our bridge is located near Wayne State University in Detroit, Michigan. It is located between M10 and M1, and the new bridge will serve as a community connector to connect Wayne State to the rest of downtown Detroit.
So the previous bridge was constructed in 1960s and was deemed structurally unsafe and no longer serviceable by MDOT. The new bridge is a network arch bridge and will be the first of its kind in the state of Michigan. The stakeholders have promised a signature bridge, so there are no horizontal support between the arches. This bridge is also designed to be used to the since it will act as a community connector between Wayne State University and downtown Detroit. A major design element of this bridge is that it must be able to accommodate for the current I-94 traffic volume, as well as to be able to accommodate for any future expansion that can occur in the next 10 to 15 years. Because of this expansion, the arch bridge is designed with no middle support. Because of the project location, MDOT decided to go with an accelerated bridge construction project and offsite construction area. The current daily traffic of the I-94 is 194,000 vehicles per day. This is a constraint because during the final installation process, there will be a week-long closure of the I-94. A major concern of this project is its location. The bridge serves indicated where the bridge is, and this bridge is 240 long and 96 feet wide, and has to be constructed in an off-site location. So, the southeast side, located by the red block, there's a parking garage that is being used by Wayne State University faculty and students at the moment. Indicated by that orange circle, there is a United South System recording studio. This is a historical site, so it cannot be disturbed by any construction. To the opposite of that, there is a motel which also cannot be disturbed by any construction. So finally, it was decided to have the offsite construction area at the Wayne State University parking lot indicated by that yellow.
Due to our project's location constraints, MDOT decided to use a offsite construction area. The bridge skeleton will be constructed in the parking lot of Wayne State University. The installation of the steel beams and concrete pillars will be supported by temporary support structures or bulkheads. 5 of these support towers will be used throughout our construction area. We decided to design the main steel girder joining arch tower. It is located at 1/3 of the total arch distance of the bridge. We chose to design this tower because the arch is constructed in 3 different sections. The base construction means that our tower must support the maximum loading for construction. We determined this critical level to be 165 steps. 2 of these towers will be on each side of the bridge, there will be 4 in total. Underneath these towers, a reinforced concrete footing is also constructed. Both calculations were determined to evaluate the structural analysis of our tower. There will be 2 different types of loading on our tower, wind load and dead load. The wind load has 2 separate components to it. 20 grips applied vertically and 26 grips applied horizontally. The dead load is the arch embracing solid base. We determined this load to be 160 meters. In order to substitute these loads into SAP 2000, the distributed loading per beam had been used. We calculated the dead load per beam to be 0.19 kits per inch, and the wind load to be 0.08 kits per inch. These roads were substituted into SAT 2000, along with the applicable LRFP road terminations, and the final design was modeled for the control of road base. Our final design, as seen here, comprises of 6 different numbers. The columns are HP 12 by 50. There are 2 types of beams used in our design. The top 5 beams are W 8 by 18 lines. The 2 side beams are W 12 by 16 lines. And the bracing of the frame is angle numbers L 4 by 4 by 3 bases. The overall dimension of our steel wallpaper is a base of 58 by 60 and an overall height of 12 feet.
So based on the loads that were applied to our frame, we designed the footing, we designed a 15-foot square footing to hold with an overall thickness of 15 inches to support the frame. On top of the slab, it will include 4 14-inch square steel column base plates to support the columns of the tower. Using riser foundation, a moment of 25.6 kip feet was used to determine the reinforcement needed to support the footing. The riser output gave us a total number of 30 number 5 reinforcing bars in both the longitudinal and transverse directions. Then, verifying that calculation, we used ACI equation 9.6.1 to determine the minimum reinforcement area for the footing. Doing all that, we found that the minimum reinforcement area is 6.92 inches squared. Then using the cross-sectional area of our number 5 beam of 0.31 inches squared, we found that the total number for our footing is 21 bars. So 30 bars is used to add additional strength to the footing.
So the steel frame was designed using SAP 2000 modeling software. We then used our own design check calculations to verify each steel member of the frame. For the columns, we selected HP 12 by 53 units. Using NIC specifications, they found that the effective equivalent length at 6.2 feet, which was less than the effective length of the column of 12 feet. So we were able to confirm that non-axis bottom control. The controlling load acting on this frame was from 385 clips using LRFP load training. This was less than the design strength of the members, which was 579. For the beams on top of the frame, we selected double 8 by 18 members. We found the distributed factor load of 3.7 kick per foot per beam. Using this, we found the moment in 46 kPa. Using NIC steel manual, we found for an effective length of 10 feet, the design moment is 496, which was greater than 46. Then we conducted a shear check on the member. We found our shear to be 18.5 kips. The design shear of this member was 56 kips, which was greater than the 18. Finally, we did a deflection check on the members using a total service load of 162 kips. We found the deflection limit to be 0.5 inches and the deflection on our member was 0.4 inches. It was less than 1. We did a similar check for the W12 by 60 members which are outside of the frame, and using these moment, shear, and deflection checks, we were able to confirm that these members were adequate for our design.
As previously mentioned, the bridge will be constructed in the offsite location. Following the completion of construction, the bridge will be moved using SPMTs into its final location. This means there will be a long closure of Interstate 54. Our team has analyzed 3 possible detour routes to reroute traffic around this construction zone. We use sustainability and solutions of idling vehicles in our determination of investment. After our analysis of alternatives, the best route is suggested. On the screen, you'll see our first detour route highlighted in blue. The green circle is our construction area, and the red line represents the length of I-94 for the proposed term. Route 1 takes 96 and 75 to reroute 94 traffic around our construction area. The total travel time for Route 1 is approximately 6 minutes, and the total length is 5.7. Route 2 is similar to Route 1 in that it also uses Interstate. However, instead of using Interstate 96, M10 and I-75 are used to reroute I-94 routes. The total travel time is 7 minutes, and the route length is 16 minutes. While Route 1 and Route 2 are using Interstates, Route 3 is a little different. We decided to reroute traffic using city-side streets. Because the surrounding area has one way, Route 3 was not able to be designed for both directions of travel. Therefore, Route 3 had to be split into Route 3A and Route 3B. Route 3A is where I found traffic. This travel time is 7 minutes and the total travel length is 2.5 kilometers. Route 3, similar to Route A, is only for one direction of travel. This is the westbound direction. It will take 8 minutes to travel 2.75 miles. These travel times consider optimal travel conditions, but with no delays happening.
In selecting detour routes, sustainability was considered. The team investigated the link between the transportation sector and CO2 emissions. According to the EPA, 29% of greenhouse gases and CO2 emissions come from the transportation sector. So finding effective and efficient detour routes for high volumes of traffic will help reduce these emissions. Studies have also shown that idle and stop vehicles increase CO2 emissions in the air. According to a study done by the U.S. Department of Energy, idling vehicles account for about 30 million tons of CO2 a year in the United States alone. So, based on this information, the team used 3 plus speed and number of stops to help select the best detour route. Routes 3A and 3B go through city streets, so they will be most affected by the number of stops versus routes 1 and 2 that use interstates as their route. Then an analysis of alternatives was conducted for each route. The team came up with 5 criteria to compare each route. These criteria are travel time, route length, level of service, CO2 emissions, and simplicity of route. After each of these categories were investigated, a point system was created to evaluate each route. Shown in this table is the criteria that we use. For level of service, we found the level of service for each road in the detour route, then came up with the average level of service as a route as a whole, which are represented in the table here. The number of stops section of the table is linked to CO2 emissions that was discussed in the sustainability portion of our route. And finally, for simplicity of the route, since we're analyzing 3 routes, and Route 3 has 2 sections, we came up with the ranking of 1 to 4, with 1 being the easiest to maneuver and 4 being the hardest to do. So based on all of these criteria of travel time, length, level of service, number of shots, and simplicity, the team then assigned a point value on a scale of 1 to 4, with 1 being the best and 4 being the worst. However, for level of service, since there are level of service classifications A through F, a point system of 1 through 6 was given, where A equals 1 point and F equals 6. Based on all the criteria and the total number of points, the lowest score represents the best route. Therefore, Route 1 was selected for the detour route during the week-long closure of I-94.
Following the completion of the design aspects of the project, the cost estimate was presented. We used RSV's estimating software to estimate the cost of our concrete footing, steel culvert, and detour routes. Some of the specific costs we analyzed were material, labor, maintenance, and equipment costs. The table on the left shows our total material costs. These are the materials for our steel culvert and our reinforced concrete footing. The total came down to approximately $44,000. The table on the right shows our total maintenance costs. These cost items are for our detour. Some of the items included detour signs and road closed barriers. The approximate total was $10,000. Labor was considered for all the cost items previously mentioned. We considered the labor to construct our steel culvert along with a reinforced concrete footing and the labor to implement our traffic control measures. The total was approximately $28,000. All these costs considered, along with mobilization, equipment, overtime profit, and miscellaneous fees, and total project costs. Calculated at $119,205 in 92 cents.
So to summarize, our final recommendation for this project is to use a 15 by 15 concrete footing to support the design steel framework. From traffic analysis, our recommended detour was Route 1. For all these recommendations, we came up with an approximate final cost of $119,000. Finally, we would like to thank our HDR sponsor, Mr. Mike Laviolette, our faculty advisor, Dr. Pura Panaikar, and our senior design faculty advisor, Dr. Dekayunis. We'd also like to thank everyone in the Department of Civil and Construction Engineering at Western Michigan University. The floor is now open for any questions. Thank you.
Questions? Did I miss it? Did you analyze the soil before you determine the 15-foot footing?
No, what we did is we had a document provided to us with this footing. So we just went through the design checks to show that we know how to do them and verified that their design will work for our structure.
Okay, so you, show me again how you did that.
Is that,
How did you determine the 15 foot by 15 foot plan?
oh, okay, so our sponsor provided us with an erection plan document, which is where we got most of our loadings from. So in their footing design was a 15 by 15 foot, 15 inches thick. So we just used their dimensions and then verified with the software we know how to use to get what we.
But you did verify with the soil data.
No, we were not provided with any soil data, so we just assumed that because our calculations came out to what theirs were, it was sufficient.
Okay.
You know, your steel erection, was it welded, bolted? Maybe I wasn't part of the project, I was just kind of curious if you guys analyzed that in your framework.
So, it was not part of the presentation, but we did design a welded connection as well. So it had, I believe, 3 boards, and it was a welded connection, this was for the frame. And, yeah, 3 boards. And then, we also designed the base plate for the concrete putting and the frame as well.
Was that a base plate with like headed studs? Or was it embedded?
Yeah.
Okay, into the concrete?
And then the connection would connect the.
The columns would weld to the base
Yeah.
plate?
I'm sorry, what's that something with the connection they did? Is it a pink connection or a fixed connection the beams with the color? We use the fixed connection as an instruction. Yeah, that's that analysis. Just that analysis, what do you see when you analyze your beam? Are you going to describe where you fill your beam, design analysis? For the beam? Yeah, so like what is, I think, what something right there for the beam component. So one of the assumptions was that, the wing acting on this frame, we decided was, we took it as a vertical load because it's an open frame. So we used the dead and wing load that was given by the sponsor. Those are the only loads acting on this frame. And we used it as a vertical load for the frame. However, we did consider moment when deciding the concrete footing. But the frame, one of those main assumptions was that the wing was not transversely but rather horizontally. Yeah, but the
The connection that is back is the same connection. What I see here is it's a part of it. Which may go in this project. And also, putting it in the product, later I will design the fix the So the connection, so I think she just saved it, but the connection is a bolted connection. So, it was
In the subtool you use the subtool recorder, right?
Yeah.
In the subtool recorder, what kind of support do you use? Thin or fixed?
Yeah, we use that bit.
Yes, we do that.
Bit.
Thin.
So I think our pictures is wrong, 'cause I think we ended up painting it. So I don't think we ended up using the well. I think everything is just simply for the question. Yes, I think we got rid of this, rounded part, we just forgot to hide the picture. So, sorry for the confusion.
Yes.
So 194,000 vehicles per day is a lot of traffic. When you consider the detour, do you guys look at what's going to happen on the detour route? When you send that traffic to the detour route,
Yeah.
did you try to analyze what's going to be the impact on that detour route?
We considered the impact of the CO2 emissions, and we also considered in our report, after you are finalizing the routes, that some of our traffic company that was from point to B, which was during the COVID pandemic, we also considered implementing a suggestion of Route 1 and Route 2 if the detour route decided to let I-96 fail. So we would suggest using the dynamic messaging boards to route half of the traffic in I-96 and the other half of it in 10, so that neither route would be severely impacted by it.
So what would be the new level of service on the detour route?
With the split route,
Yeah, once you send traffic to the detour route, what would be the new level of service on that detour route? Do you look at that?
So the level of service that's shown in this table is with the new traffic. So we did not go into the analysis if we end up splitting it, we just chose the best one. So we have a disclaimer in our report saying that we realize traffic counts for year 2020 are really low because everyone was voting from home. So we then decided that 2 routes would be able to help if the level of service with the accurate data, pre-pandemic numbers, make a route fail. So we can then split the traffic in half and represent 2 different routes. So the route fail.
Any final questions?
Hello, Jerry.